Hello, everybody. Let's do a complete walkthrough of the solution approach that I proposed for problems like this one that are maybe too large or complicated to analyze directly. So we started off by brainstorming different ways that we might try and analyze this directly. People suggested splitting it into 6 triangles, figuring out how many dots in a triangle, and then multiplying that by 6. Some people suggested count the dots around the perimeter and then look at one hexagon smaller and add up that perimeter. So it's like you're adding up all of the nested perimeters separately. And all of these approaches are perfectly great and will work. But the target idea that I want you guys to think about is this. If you have a problem that's too large, imagine the smallest possible version of that same problem and look at that one. And then one that's one larger and one larger and one larger to collect data. So here's how that might look. What we're really interested in is, if we're going to make a data table, the original problem, there were 22 dots along each side, and I want to know how many dots total. But that was too difficult to figure out. So let's imagine going all the way up on the table and start with a very small side length. What happens if we've got just one? Well, there's only one dot. Okay, let's make one larger version of the problem. Here you can see every side has 2 dots along the side, and we can count up how many dots there are. 1, 2, 3, 4, 5, 6, 7. So side length 2, there's 7 dots. Here we've got, you can see this same shape nested in here. And then I've drawn another one with a side length of 3 around the outside. So I'm going to take those 7 dots in the middle and add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that gives us 19 dots. So at this point, you always have to ask, like, do we need more data or can we start looking? So we know that there's some equation that generates this data. Is it a linear equation? Is it an exponential equation? Well, we can look at the growth and see what characteristic kind of growth matches the data that we have. So here, this looks like plus 6. This looks like, what's that? 12. We don't have quite enough data yet, so let's do one more. Okay, so I've drawn another diagram. You could just count them. You know, you can also start looking for patterns here. So I know I've got 19 on the inside. I need to add the number of dots on the perimeter here. I see that there are 3 dots along the side plus the 4th, but I don't want to count that one extra. So I can group them in groupings of 3. And then the 4th one will be part of the next edge. So you can see I've got 6 sides, so 6 groups of 3. So altogether, that's 19 plus 18 is 37. And we said this was plus 18. So now I've got enough data that I am starting to see a pattern. The first order growth isn't constant, but it looks like the second order growth is constant. So now we'll enter phase 2 of the problem solving. Now that I know that the second order growth is constant, I know that the equation is a quadratic. But I don't know what quadratic. You know, is it x squared plus 5? Is it 3x squared minus x plus 7? I just don't know. So I'm going to write the most general quadratic I can. It'll look like some number of x squareds plus some number of x's plus some constant on the outside. So A is going to be the number of x squareds, B will be the number of x's, and C will be my constant on the outside. So what I know is that there are 3 numbers, A, B, and C, that will produce the data in this table when I plug in those x values. So when I plug in 1, some combination of A, B, and C should give me 1. And then when I plug in 2, it'll give me 7, and so on. So what I'm going to do is I'm going to choose the first 3 points here. I'm going to plug in those x, y values and see what equations I get. So here when I plug in 1 for y, I'll put the 1 there in the y place. Then I'll plug in 1 for x. So a times 1 squared is just a. B times 1 is b. And then c is just itself. Okay, let's plug in another point. So here the y value is 7. I'll plug in the x value of 2 into this equation again. So a times 2 squared gives us 4, so there's 4 A's. 2 when I plug it in for x here gives me 2 B's, and then there's C. Let's do another one. So I'll plug in 19 as the y value. I'll plug in 3 as the x value. 3 squared is 9, so there's 9 A's. There's 3 B's, and there's a C. So now I need to figure out A, B, and C. I've got a system of these 3 equations, and so now I can do some algebra to solve. I'm going to follow the same steps that I did in the notes. So I'm going to combine the top 2 equations and eliminate C. So I'm going to subtract the top equation from the middle equation. So 7 minus 1 gives me 6. 4a minus a gives me 3a. 2b minus b gives me b. C minus c gives me 0. Okay, now I'm going to subtract the middle equation from the bottom equation. So 19 minus 7 is 12. 9 minus 4 is 5a's. 3b minus 2b is just 1b. And then c minus c is 0. Okay, now I'm going to combine these two, again, by subtracting them so that I can find a. So 12 minus 6 is 6. 5a minus 3a is 2a's. B minus b is 0. So that gives, so if I divide both sides by 2 here, I've got that a is 3. And the a that we're talking about is how many x squareds. So now I know part of the equation. All right, let's plug that in here and keep going. So I'm going to take the same equation, 6 equals 3a, except now I'm going to plug in the value that we know for a. So I'll subtract 9 from both sides. So 6 subtract 9 is minus 3. So I know that b is negative 3. So now I'll plug both of those into the original equation. So the original equation was 1 equals a, which is 3, plus b, which is negative 3, plus c, which I don't know. But 3 minus 3 becomes 0, so that gives me that c equals 1. So putting it all together, I now know the equation that produced my original data. The equation is 3x squared minus 3x plus 1. Oops. So if we wanted to know the answer to the original question, which was how many dots are there when there's 22 dots on a side, we'd plug in 22 for x. So it would be 3 times 22 squared minus 3 times 22 plus 1. And we'd probably break out a calculator and calculate what that is. And that's how you would do it. So again, it's not the only way to solve these kinds of problems, but it's a particularly useful one. And the rest of the in-class problems had you practice looking at the big complex scenario and then imagining what's the smallest version of that problem look like. And then you make it one larger and one larger and one larger to collect your data. You look and see what type of growth does it look like. Once you know what type of equation you have, you write the general form of the equation. Then you can plug in all the xy coordinates that you know are in your data to get 3 separate equations that you can then use to solve for what values of a and b and c will actually give you the equation that produced all your data in the first place.